Now you can see half power frequencies and bandwidth calculation point of view. Uh, First you can take in what is the average power. So average power consumption in the AC circuit you can take in HPS. So E RMS into I RMS into cos pi. E RMS into I RMS into cos pi. Where cos pi we need to take in resistance divided by net impedance. Net resistance divided by net impedance. I RMS. So you can take in E RMS divided by ERMS divided by net impedance. So that is the known formulas for this. P equal to IR. Now you can substitute the IRMS and ERMS values over here. Then you got ERMS. So ERMS into IRMS value, that is ERMS divided by net impedance times of cos pi is nothing but resistance divided by net impedance. So finally you got ERMS square divided by Z square times of resistance R. So here average power will be depends on ERMS Z square net impedance value and resistance. Further you can extend this one. So ERMS the square times of R divided by Z square is nothing but R square plus L omega minus 1 upon C omega whole square. So that is your uh, net average power consumption, that is R square. So Z square value is R square plus L omega minus 1 upon C omega whole square. Now it is clearly we will note that average power will depends on, or average power depends on angular velocities. Angular velocity. So see here, if angular velocity will approach us to zero, or our angular velocity is approximately taken as to as infinity, then these terms belongs to infinity values. If you take an omega equal to 0, so this term will become 0, then total denominator will become 0. And omega equal to infinity, then this term will become infinity. Then total denominator will be infinity. So anything divided by infinity, you got 0. So if angular velocity equal to 0 or angular velocity equal to infinity, then then average power consumption equal to 0. There is no doubt about it. Average power consumption equal to 0. And if you take in one more point, if you take in, so if L omega equal to R omega at resonance. So if L omega equal to R omega at resonance, at resonance, so L omega that must equal to 1 by C omega. L omega that must equal to 1 by C omega. Then Z square, Z is maximum value. Z will become maximum. So in this, so Z will becomes maximum, that is the net impedance is R only. So therefore, we got maximum power. Then average power will be maximum. So average power will be maximum. That value you can take. So E RMS square times of R divided by Z square value you can take as an R square. Therefore, R and R get cancelled. Now you got a maximum power is E RMS square divided by resistance R. But in other all the cases, average power will be depends on frequencies. Now, half power frequencies is nothing but frequencies and the power will become, that's it. Now here you can see average power consumption HPF. So half power frequencies, that is nothing but frequencies. So frequencies where the power frequencies where the power where the power is half the maximum power, is half the maximum power. So now you know that maximum power consumption, that is E RMS square divided by 2. Now the power formula, so you can take E RMS the square divided by z square times of r at any instant of time. Now the power will become half the maximum power, or power you can take as to be as, so ERMS whole square divided by z square value. So r square plus L omega minus 1 upon C omega whole square times of R. This power will become half of the maximum power. So P max divided by 2, where P max is ERMS is divided by 2 na? ERMS divided by, so ERMS value is, power maximum power is ERMS square divided by resistance R. Now here you can see. So maximum power is half times of maximum power is, so ERMS square divided by net resistance, that must equal to, so ERMS square times of resistance divided by R square plus L omega minus 1 upon C omega whole square. Then ERMS square and ERMS square get cancelled. So if you are cross multiply this equation now, so you got R square plus L omega minus 1 upon C omega whole square, that must equal to 2 times of R square. Or further if you are extended now, so L omega minus 1 upon C omega whole square equal to R square. So here you can take in two different types of cases. See, case number 1. So here, so L omega minus 1 upon C omega, that must equal to plus or minus R. So from here we need to take in two different cases. First one is L omega minus 1 upon C omega, that equal to plus R1, and one more L omega minus 1 upon C omega, that must equal to minus R. If you solve in these two quadratic equations, you got two different types of values. That values you can take in half power frequencies. So now you can see, so multiply this equation on both sides with, so multiply the equation with on both sides with omega divided by L on both sides. So then you got omega square minus 1 upon LC, 1 upon LC, that must equal plus omega times of R divided by L. Now you can take in omega square minus R divided by L times of omega minus 1 upon LC, that must equal to 0. It is the one equation. And here also you can multiply with omega divided by L on both sides. So here you got omega square minus 1 upon LC, that must equal to minus R divided by L times of omega. From here you got one quadratic equation, omega square plus R divided by L times of omega minus 1 upon LC, that must equal to 0. Consider only positive roots. So consider only positive root for frequency. That you got lower frequency and upper frequency. So from the first equation, so taken omega only positive values, from the equation. Already you know that omega is the root of quadratic equation minus b, that is R divided by L plus under root b square, that is R divided by L whole square minus of minus plus 4a. 4a value is 1, c value is L divided by C, 4AC divided by 2A. So it is 2A value is 1. So it is a one angular frequency taken this high, first higher value of half frequency. And here you got lower value of half frequency. So minus R divided by L. So plus under root B square, that is R square divided by L square minus of minus plus 4 divided by LC divided by 2 times of A, where A value is 1. So now this value you can take an higher value and this value you can take an lower value. So you can take an WH and WL be the half power frequencies. Okay. For the quadratic equation in omega, if you are consider only positive values, na, then you got lower value of half frequency and higher value of half frequency. Now bandwidth is, so now you can take in bandwidth. So bandwidth, if you are taken, the difference between the frequencies at the maximum power, the differences between the maximum powers you can take as Vs, uh, the difference of the two frequencies, the difference, the differences of the two frequencies at maximum power. At average maximum power, you can take in as a bandwidth. Therefore, bandwidth you can take in delta W, that is omega higher minus omega lower. Now, omega higher is value is nothing but, from this equation, omega higher value is nothing but R by L. So, copy that formula, R by L plus under root of R by L whole square, R by L whole square plus 4 divided by LC, minus of minus plus R divided by L minus under root R square divided by L square plus 4 divided by LC whole upon 1 by 2. So just common out 1 by 2 on both sides. Now these two terms get cancelled. So you got, so 2 times of R by L into 1 by 2. Therefore, R get cancelled. So you got a bandwidth is nothing but resistance divided by inductor. That is the delta omega. That is the bandwidth of the circuit. So bandwidth of the circuit. Okay. Now here only we will define one more term also, that is a quality factor. So quality factor. So we can define the quality factor as ratio of the resonance frequency resonance frequency to the bandwidth. Okay. Already we know that the resonance frequency, that is you can take as omega naught divided by bandwidth, you can take in delta omega. So resonance frequency you can take at resonance frequency Xc must equal to XL. So therefore 1 upon C omega naught, that must equal to L omega naught. From this equation, omega naught you can take in 1 upon under root LC, and bandwidth is nothing but L upon R upon L. Therefore 1 upon under root LC into L divided by R. 1 upon bandwidth, na? Therefore L divided by R. So therefore you got the formula is 1 upon R times of under root L divided by C. That is the quality factor. You can take in Q factor. Okay. So copy this formulas. So in this video, I am given the concept belongs to half power frequencies, and bandwidth, and along with that one quality factor also. Okay. Now see wattless current and skin effect in parallel resonance circuit, or you can take as well as a rejector circuit. For this current, already you know that the average power consumption in AC, that equal to, so ERMS into IRMS cos pi. Okay. Now for any circuit you can take in reference frame is ERMS. Like this you can take in ERMS, and in this direction if you take as a IRMS. Okay. Then angle between them you can take as a theta. Angle between them you can take as theta. Now current we can resolve into two different components, that is one is along the ERMS, that is I RMS times of cos pi and perpendicular to E RMS, that is acting in this direction, that is I RMS sin pi. Now here you can see, because of I RMS cos pi, due to I RMS cos pi, power will be maximum. So average power will be does not equal to 0. Why? Because average power will be depends on IRMS cos pi. But but due to IRMS sin phi, average power consumption equal to 0. Average power consumption equal to 0. Hence, this IRMS sin phi current you can take as a wattless current. Wattless current means because of this current, power production is not there. So because of this current, power production is not there. Such type of current you can take as a wattless current. And because of IRMS cos phi, power will be does not equal to 0. That's for IRMS cos phi you can take as wattful current. This is the spin effect. Spin effect is, so it is just we need to understand the propagation of a current through the conductor. Let us you can take in it is your conductor cross section, and the alternative current will be in case of DC current. So first you can understand in case of DC current. DC current definitely passes throughout the cross section. DC current passes throughout the cross section because of there is no opposing force. There is opposing nature by the conductor. Conductor point of view or non-conductor point of view, DC current will be traveling throughout the cross section. But alternative current point of view, current does not traveling throughout the cross section. Current will be moving up to certain depth only. So after this one, because of induced EMF inside the core, so that is opposing the your current for EMF. In this core, current alternative current will passes across the circuit equal to 0. So, and in this region only, amount of alternative current that is not equal to 0 means up to certain depth alternative current, up to this region alternative current will be passed. Alternative current does not traveling in the region, therefore that effect you can take as a skin effect. Okay, the distance or alternative current will be traveling up to certain depth into a given conductor. It does not flow uniformly in the conductor. Such type of effect you can take as a skin effect. And the distance you can take as a skin depth. So the depth, the depth up to which, up to which, the depth up to which AC current flows, AC current flows, AC current flows through the wire, through the wire is called is called skin depth. Is called skin depth. Denotes with rho. It will be depends on nature of the medium. See, next concept, a rejector circuit. Rejector circuit in the sense now, if you take in one inductor, so one inductor and one capacitor. So these two, if you are connected parallel to each other, maybe here I am taken ideal inductor. So if you take a non-ideal inductor also, it is accepted. Like this, if you are connecting to one alternating source, connecting to one alternating source, and inductance you can take as L and capacitance you can take as C. Amount of EMF you can take in E equal to E naught sin omega t. Now, amount of current traveling through inductor, maybe phasor diagram if you taken, it is your reference phasor, and amount of current passes through inductor having a negative phase. That is, we can take as IC and having a negative phase. That is already we know about in the circuits. And amount of current passes through capacitor you can take as positive, that is IC having a positive phase. IC if you take as a positive phase. Now amount of current traveling through inductor equal to amount of current traveling through capacitor, na, the net current across the circuit equal to 0. Such a state is called as a resonance state, or such a rejector is called as a rejector. Such a circuit is called as a rejector circuit. See the condition. So if amount of current traveling through capacitor, that must, if it is equal to amount of current traveling through inductor, then then net amount of current traveling across the circuit, net amount of current traveling across the circuit equal to zero. Such circuits, such circuits. So you can take next way as a rejector circuit. Rejector circuit. Okay. Now you can see the condition. IC is nothing but amount of EMF applied. So E divided by, so impedance due to capacitor, that must equal to EMF due to impedance due to inductor. Now if you are comfortable with this equation, E and E get cancelled. Amount of impedance due to capacitor equal to impedance due to inductor. Impedance due to capacitor is nothing but 1 upon C omega. That must equal to impedance due to inductor is L omega. At rejector circuit is in resonance condition. Therefore, from this equation, resonance condition, angular frequency you can take in omega naught, that equal to under root 1 upon LC. So at resonance rejector circuit is in resonance condition, then current does not allow by the circuit. Okay. So if it is non-ideal inductor, so here I'll given one simple case. So case 2, and if you're taken, inductor is non-ideal, if inductor is non-ideal, then so inductor having a certain amount of resistance and having it is your inductor. Now this combination is connected to capacitor. Now, so this same circuit is connected one alternating EMF source. Then your angular frequency at the resonance condition is will be changes. That is directly I am given a formula. So that is omega naught equal to under root of 1 upon LC minus R square divided by L square. So like this, resonance circuits, rejected circuits will be working in AC. So simple term point of view, at resonance, at by the rejector circuit, net current across the circuit equal to zero. Why? Because the current traveling through inductor and current traveling to resistance, that is capacitor, will be equal and opposite. Therefore, net amount of current passes across the circuit equal to zero. Such type of circuits you can take as well as a rejector circuits.